Hello, so my name is Stanley C, and I'll be doing a demo on my MCO1 for Perceptron and MLP. Before that, I would like to apologize in advance for not being able to turn on my camera because my screen was flickering whenever I turn on my camera and while I'm sharing my screen. So I'll start. So I'm gonna be starting with a simple experiment on the AND or NAND nor an XOR operator. So where I'll be using that specific Boolean operator for the expected output. So in here I have 1,000 cycles in or iterations in total. And as you can see, it's like flickering, but yeah, with two input values where x1 and x2, and then with corresponding weights, and then also with the bias x0 and w0. And for the expected, since for example, I'm using an AND, so in an AND operation, both inputs should have a value of true or should have a value of 1. So if both values are 1, then I can just get the sum of them, so equals to 2. So it means that if x1 plus x2 is equals to 2, then it's a true for an AND operator, and otherwise it would be false. The activation function here, the activation value in here is actually the sum of the products between x and within the input and its respective weight. And then the output value is just the comparison of the activation value. If it's greater than a threshold of 0, if it's greater, then it will give a value of 1, else 0. And then the error is just the expected output minus the actual output. For the new weights, this will be actually the old weight plus the product of first is the learning weight, and then times the error times the data. So for new W0, it will be times the data of x0, and for new W1 times the data of x1, and so on until the new W2. So this is how it looks like. I'll just go straight to how it goes in OR. Actually, in before that, you can see that the weights, they actually stop learning after some iterations. I think at this point it stops here at iteration 51. Then it just goes the same until the end of the iterations. As for the OR, since for an OR operations, one of the values should be true, then we can just do a reverse logic on that, where if the sum of x of the input is 0, it means it's false, else it's true. So from here we can see that the weights stop learning until probably at this point here, after the 74th iterations, from 75th iterations going down until the 1,000 iterations, it actually stays the same value. So the weight stop learning at that. And then for the NAND, it's the opposite of the AND. So basically, when you see there's when both of them are true, it will become 0 and true otherwise. So similar behavior we can see in here, that after a certain number of iterations, and this case is 93 iterations, the weights remain the same until the end of the 1,000 cycle or iterations. As for the NOR, it's behaved the same way, where if it's the opposite of the OR, and can see that the weights stop learning after, I guess in here, the 46 iterations, and it stays 0.02, negative 0.09, and negative 0.03 until the end of the 1,000 iterations. However, the only difference is on the XOR, actually, because XOR is slightly different from the rest, and we can see that the weight never stopped learning until the end, and it keeps on, the weight keeps on changing, and as if it keeps on learning. So how it looks like, it's like this, somehow looks like this. So for the AND, NAND, OR, and NOR, you can actually see that after a few iterations, the weight remained on the same line until the end of the 1,000 iterations. However, for the XOR, we can see there's like a flow, like each or like every line keeps on moving up and down, up and down, up and down. So the weights kind of keep on changing. So it never really get to the point uh, where it stops learning, but it keeps on changing, changing, and changing. So, and looking at this actually kind of reminds me of the loss function when we were doing deep learning. So kind of look like how loss function works, but in this case, loss function actually keep changing, but in a very small pace. But looking at this feels like I'm looking at a loss function in a way. Anyways, for my next experiment, I'll be experimenting on the animal data set. This has 10 categories: amphibians, birds, cnidaria, crustacean, fish, insects, mammals, mollusca, reptiles, and a special category where it has, I think in total, there are 43 features in total, and with its name in here. So first, I'll be trying to classify if an animal is cold-blooded or warm-blooded. So but for this case, I'll be just using the column for the cold-blooded in this case. So, and I'll be using the 4 first features, which is hair, scales, feather, and moist skin. So I noticed that for cold-blooded animals, they would actually have, it's like an OR operator between scale and moist skin. So for some animals have only moist skin, and then it's cold-blooded. Some animals only have scales, then it's cold-blooded. And some animals have both scales and moist skin. And for feather, I don't think there is an like an animal that has a feather like for this one, but it's a cold-blooded. So I think feather is one of the features that we can use to see if an animal is cold-blooded or not. And as for the hair, sometimes it appears in case such as insects in here. You can see that insects are actually cold-blooded animals and they have feather, or I mean hair, sorry. I mean, they have hair. But as for the rest, usually most of them are usually either have scales, moist skin, or have both scales and moist skin. And on some other special cases is where this crustacean category, where it does not have any of the feature, but they are still a cold-blooded animal. So going back to the part earlier. So since I think Cnidaria does not hold any values for either cold or warm, it's not either cold or it's not warm-blooded. So I decided to remove it from the training, from the classification actually. So, remove the data from the classification so that it won't affect. There will be no data that is not supposed to be there. So for the cold-blooded, I'm using the hair, scales, feather, and moist skin with the same 4 features without the cnidaria type. So I separate the data into 90-10 train test a percentage, where I use part in here to just split the test and then save it in the Excel test and then Excel train test, and then I just copy each all the values for train in here, and then all the value for test up in there, and then the weights that I'm using for testing is just the latest weight from the training. And surprisingly, I got a pretty good result of around 80% for test accuracy, and then 81.71% for the train accuracy. And if I try to modify this further, like changing hyperparameter and stuff, and it won't really increase the test accuracy anymore. And I think this might be the best one that I have so far, because let's say I'm changing this one to a relatively high one, it actually reduced both train and test accuracy to by 10 significant value. That's why I decided to. That's why I think that this might be the best configuration already. Then moving on, you can see that this is how the test and train look like. This is with Perceptron. So let's try with multi-layer perceptron and see how it goes. So in the multi-layer perceptron, I actually just did the same thing, but this time I just loaded it, and then from data frame form, I converted to NumPy and then to tensors after that, and require a grad true so that it can do back propagation, and put them all in the GPU. And then I use a batch size of 8 to do for the training. And then for the network, I use 2 hidden layers with size of 256 for each layer, and learning rate of 0.01 with a activation function leaky relu on each hidden layer, except for the last one that goes to output layer. So, and then in here we can see that from training alone, it gives pretty much slightly better accuracy of 85%, and the train does not look that many losses were like the losses are not decreased by not that many. And then although the train accuracy keeps growing up, but the test accuracy is still not very good. So I thought maybe it's because I'm using like not all the features, because in here I'm using only 4 features to classify if it's cold or blooded or warm blooded. So on the next classification, I decided to use all the features. So there will be around 41 features, I guess, except for the cold-blooded and warm-blooded. So, and with the labels being only the cold-blooded. And this is the same data set where I excluded the Cnidaria animals, following the same format. So transferring them to tensor and then to GPU after that. Then I try to do a simple perceptron with PyTorch. So just one linear layer and then with a leaky relu output within the perceptron, and the performance are actually not that bad. For the train accuracy, which is this 98%, and for the test accuracy, I get 90%. So it's actually not that bad with one perceptron alone. And maybe it's because of the leaky relu, possibly because of the relu activation functions that we have on the lab after the last layer, unlike the plain perceptron in here that we just use if it's only greater than a certain threshold or not. And then like the one in the Excel file, I mean. So, and then for this one, I tried the multi-layer perceptron and using this almost the same configuration. So two hidden layers with little leaky relu activation after each hidden layer, and then I'm using a hidden layers of hidden size of 512 and the learning rate of 0.05. And I think I'm using this same learning rate as well to make sure that as much as possible the comparison between the models are almost the same. And then after that, from here onwards, I think on the 60 epoch, I already get 100% accuracy, and you can see the loss function goes down. Accuracy, there's a slight jump in slight drop in the accuracy, but it keeps on growing up. And then and I found the test accuracy to be 100%. So can say that MLP is actually really performing better than a single perceptron. And then we go to the next classification problem, which is the next one, which is where I try to classify a carnivore, herbivore, and omnivore, where I set the label to just 0, 1, 2. And this time I used the train and test data set. So this is also included with the Cnidaria animal type. And in here, I just created a new column for the data frame. So if it's a carnivore, then just make the animal type to 0, animal type. So I'll be using the animal type column as the target or as the ground truth. In this time, I'm using all features except for the carnivore, herbivore, and omnivore. And then for labels is using the animal features, and I got 40 features in total. So doing the same thing, I transfer it to NumPy and then to Tensor, and then putting it in the CUDA GPU so that it can train better from there. And then same thing with the Perceptron. I'm using a single layer, but this time I'm using a 0.01 learning rate because it's much faster that way based on the experiment, and it reach sorry, it's not much faster. It performs better that way based on the experiment. And I'm using the cross entropy loss for I think almost all my experiments. And in here we can see that it got up to 81.82% on the test set with just a single perceptron. And if we see on the multi-layer perceptron part, I'm using 3 hidden layers and Librelu after each active hidden layers, and then almost same configuration, same learning rate, but I use a hidden size of 512 for each hidden layer, same loss function, and then I got an accuracy of around 81.82. So this is where I'm actually thinking, why is Perceptron actually can the performance is comparable with the MLP, unlike the one before, even though it's like from 90 to 90% and 100%, it's still big improvement from like a 10% improvement on the performance is actually pretty good. But at this point, the accuracy is actually the same. Like the test accuracy is actually the same, and you can see if you see the training accuracy, it's actually pretty similar. Only slightly higher, yeah, kind of higher for the MLP, but in the test, they still yield the same test accuracy. And this is where and actually before this, the test accuracy of the Perceptron was actually better than the MLP. And then I tried to fine tune the hyperparameter, and I wasn't able to get any more higher than 81.82%, which is actually so like the same performance, I guess, for both MLP and Perceptron, which kind of interesting when I try to look at it further. And then for my last classification is I use all of them, so all features, and then I use the categories to target. So using the same train test set, and then converting all the category into the index using the index of this one. So I think the labeling here is wrong. I'm sorry for that. Zero is, in this case in here, 0 is actually reptiles, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for features, I'm using all of them. And then as for this one, I'm using the same method over and over, just from data frame to NumPy and then to Tensor. After that, I put it in the GPU. And then for Perceptron, I'm using the same configuration, just tweak the learning rate on this one. So from here, I get an test accuracy of 40.91% in this case. And this is where I see a significant performance improvement. Like aside from the first classification, the 90 to 100%, this is actually a more significant improvement for the MLP, because I'm only using 2 hidden layers, Leaky Rail activation function with 512 hidden size, same learning rate. And when training, I was able to achieve the 100% accuracy. And you can see in here that the accuracy actually keeps going up, although there's a slight flickering at this point. But for the test, it actually reaches 100%, which is shows me how powerful MLP really is as compared to a single perceptron. So the next thing that I want to show is the MCO1, which is actually the digits classification using the MNIST dataset. So the MNIST dataset is actually composed of 60,000 train set and then 10,000 test set. In this case, I try to find if all the data are balanced, like distributed well well balanced, because after this experiment on the MNIST dataset, I'm actually surprised that I got a very good result. Like even on my first try, I got, I think, somewhere around 95 or 93%, and then just a slight tweak here and there for the hyperparameter, changing the hidden size, learning rate, and stuff, and I was able to achieve 97 to 98%. But I could not get any higher than that, no matter how many I tried to, how much combination of hyperparameter tuning that I tried, which maybe there's some part that I was not able to tweak for the hyperparameters. But if you look at the shape of the size of the image is actually 64 in here is for the batch size, and its single image is actually 28 times 28. So this is how it looks like. The size of the image is actually 28 times 28, and then this is how the pictures in the sample look like. So ground truth of 2 looks like this, 7 looks like this, etc. And then for the model, I mostly use this is after a few tries, so I'm trying using this and that, and I think this is the latest try I've been, but I also got 97-98% on this part. So I think you can see on the testing down here, 98.66% with 4 hidden layers, hidden size of 512, and leaky ReLU on each hidden layer. Then using the cross entropy loss and the Adam optimizer. And one thing to notice for the animal dataset problem, because I heard that using Adam as your optimizer is actually the best. People said it's the best optimizer for deep learning and stuff. So I tried that actually with simple MLP in the animal dataset, and it actually performed not quite good. I'm not sure why. So I decided to stay with the SGD as the optimizer, stochastic gradient descent as the optimizer for the MLP experiment on the animal data set. But for the MNIST data set, I'm using the Adam as the optimizer with the learning rate of 0.001. And then this is for the training. So for each training, the losses is just computed, the loss of each item times the data size, which is 64 in this case for the batch size. So each loss is each loss on each iteration on this part corresponds to, let's say, represents the 64 samples in the data set, and then loss backward, and then optimize that step. And then in here, I'm just getting the average losses for each epoch so that I can get the average loss in one epoch. So that's what I'm doing here. And then you can see that the loss decreased quite significant from 0.24, 0.3, and then up to 0.011 or 0.012. And then the train loss graph looks like this. And for the testing, what I did in here, I just did test loader, and same thing as the this one. I changed the size of the data into the image size times 2. So it's since it's 28 times 28 for the image size. Same thing in here, and then testing the model, and then this is same way to test the loss as what I did before. However, this one is using torch.nograd so that there is the weights won't be changed when I did the computations. And then for this one, the value in here is actually the result of what we have from the output, the maximum, actually the maximum, and then the prediction. And then for the prediction, it will give you either a 0 or a 1 or a 2 until a 9. And then at this part, I'm just counting. So for each label, for label 0, how many correct data, and then this is the class total for each label or for each classes 0 to 9. And then after the testing, you can see that in total class there's 175. I think it is 0, 1, 2, 3 until 9. And then we can see that it performs not bad, and like it gets it right for most of the test samples, and with average trained loss of this one. So 0, 1, 2, 3 until 9, and it can see how many are correct for each classes. And the overall accuracy is actually just averaging this 10 test accuracy. So this brings me to the hyperparameter tuning. I put here multiple ways. So for first, what I did is starting from the activation function. The learning rate in here is actually not 0, but it's 0.01. I'm not sure why the preview looks like this, but this is the actual value. So all of them are 0.01. Oops. And then this one is 0.05 back to 0.01. So just trying to see if what actually affect the performance. So with hidden layer 3, I think this doesn't have this all the same. I have all the same except for this part. They are slightly different. I will go to that. But and this part, what I changed, I tried using sigmoid, since compared to ReLU and Leaky ReLU, I think ReLU and Leaky ReLU should perform better than sigmoid. So I tried using sigmoid, and I actually got the same accuracy, like around on every hyperparameter configuration. I try to run it 3 times to get like a range, like how close can it get. And actually, it surprised me that I can still get from 97 to 98% for the accuracy. And then trying again with same configuration but different activation function using ReLU, and I'm still getting the same thing. So it's the accuracy, the test accuracy is around 97 to 98% again. And then maybe after that maybe the batch size is the problem, but using the batch size itself, I'm still getting almost the same result, around 97 to 98%, although there's a slight difference in the decimal points as for the maximum and the minimum. And then I tried the same thing, same configuration with the one on top here, but with this time with Leaky ReLU, which is the training set 3, and I'm still getting the same thing. But this one, I think it yields the best accuracy for this one. And then I tried also changing the batch size when we're using Leaky ReLU to 32 instead, and I still got approximately the same the same overall accuracy, around 97 to 98%. Then I try using only one hidden layer, because I thought maybe because I have 3 hidden layers, maybe that's why it's a problem. But actually the hidden layer itself also gives me 97 to 98%. And then I try with more hidden layers with on train set 6, and this time it actually gives me 98% for all of them. And maybe if I test it further, I might find a 97%, but based on the 3 times training the model fully from the start, it gives me the 98% overall accuracy. And then in here I tried changing, I think the last 2, I tried lowering the learning rate, and think this is still yield the same thing. And I'm starting to think maybe it's because of the number of epoch that I used. And then using a slightly higher, which is 0.05, this is where it actually reached 96% for the first time. And it actually surprises me, like maybe 0.01, 0.001 is actually the best learning rate configuration on this matter. And then the last part, I tried to train it with lesser epoch, only 10 epoch, and it still gave me a comparable performance as compared to the other, which is around 97 to 98%. So it kind of baffled me that each configuration have almost the same yields the same results. So I'm thinking maybe because maybe the data distribution is pretty good, or maybe yeah, the data distribution between the test and training set is actually very balanced, unlike the train test set that we did in here. Because no matter how much I tried to balance the train test split at this part, it actually still end up being not very balanced. Like for example, for the cold-blooded, sometimes I have 90 and 80 or 90 or and 70 cold-blooded and warm-blooded. So it's like very not really how do you call it, not really significant, I guess, because the I mean, not really significant. It's more on there's a significant difference between the number of classes, the number of samples for each classes for each class. And I thought maybe for the MNIST data set, since I think this data has been one of the longest deep learning data set available out there, and it may have been already improved and like over and over and again. And I think Jan Lekun was also part of the one who created maybe or polished its data set, because I saw his link on the link to download the data set there. But anyways, that's what I get from the MNIST data set, and it's actually pretty interesting. And I save all the models in here for each training set, because after this I'm going to do an inference to the model, because well, testing it only from the test set might not be the best scenario on this one, because maybe there's still some other things that I'm missing. So I decided to create another set of numbers. I'm not sure. I hope you can see this. I think you should be able to see. Yeah, you should be able to see this. This is another train, a handwritten digit that I draw using my mouse on Paint. So this is the original one. I think this is around 200. Yeah, 200 times 200 pixels, and then I resize it to 28, which is the same value. Yeah, the same value for the image size in the MNIST data set. And I try to mimic the background as much as possible, like dark background, white font for the color. And then this is just the handwriting that I wrote using my mouse, with two different types of digits on every for every digit, two samples for every digit. And I put it in here, and interestingly, I got the best. These are the best models that I found to be I guess performing better compared to the other, with almost the same, I think almost the same number of wrong predictions, and very less. I think they only have like 5 wrong predictions on each one of these. Let me check down here. So I think the only one is wrong is 1, and then 2, 3, 4. Actually 4 wrong prediction. So this is the image from here is actually the image from this point. I tested it one by one, and it returns to me the just the prediction using this value in here. And then I just print the prediction with the file name. So file name 0 means for class 0. And then if you can see for the first part, specifically, it predicts it as 4, which is kind of interesting because maybe there's this sharp, almost like a sharp corner at the top. Maybe that's why it considers it as 4. But for the rest, let's say for 6, actually, one of them, I think the sixth one, it considers it as 5. So maybe because I did not I intentionally not make this to be a connected line in here. If you can see this, actually, let me open it. This one, you can see, if you can see, the line in here is actually not connected. The 6 in here is not connected. So I'm not sure, maybe that's one of the reasons why it classifies it as 5. And then this one in here, the 7, it classifies it as 2, and this is the 7 with a tie. If my mom always said it's a 7 with a tie, so it looks something like this, yeah. So maybe it looks in here and it see this corner in here, so it thought maybe it's a 2. And then for the 8, the 8.2, it predicts it as 3, which is this one. 8.2. It predicts this one as 3, probably based it on this part only, and then yeah, it ends up being 3. And actually, there are many cases. Let me try to use another model. Maybe let's use the T2, T1 from training set 1, and then the second last model. Then let me quickly check what's the configuration for that model. I think training set 1, that's 3 hidden layers, so I'll delete one of these. And then learning, we don't need that. Yeah, I think that's all. Then I'll load the model, and then I'll do the same test from here. Just give it some time to load. So this is how it looks like. And in here, there's actually 1, 2, 3, 4, and 5 error in total. With in here, actually for the 8, it predicts all 8s as 3. Same thing for the 7 with the extra line. It predicts it as 2. And then the 5, actually, it actually predicts it as 6 for the 6.1, the 6 that is not connected properly. So 1, 2, 3, 4, 5 errors from 20. So 15 over 20, that's around 75% for the overall accuracy. So yeah, I think this is a sample that I can a sample, and also this concludes my demo for the MCO01. And it's actually interesting how it performs well on the test set, but when we use data that is out of the data set, like the data in here that I just made, and it lowers the performance, well, not quite significantly, since 20 data points compared to 10,000 data points is, you cannot really compare it. But it's even though with this many data being trained, it is still cannot classify it properly. Maybe because there's some flaw in how I fine-tune the hyperparameter. But overall, it's actually a great experience. It's a great great insights to see that how you cannot just rely on the test, like the test data set, because usually I will be like very happy to say, oh, okay, like almost 98% test set on almost every hyperparameter configuration. So like that concludes that my model is good, and apparently it's not. And when I try to inference the model, this happened, and you can see that there's actually some errors that the model is still making in the end. So that's all for my demo for the MCO1. Thank you.